Jantar Mantar is a collection of 19 astronomical instruments built by the Rajput king Sawai Singh, the founder of Jaipur, Rajasthan. The monument was completed in 1734. It features the world's largest stone sundial and is a UNESCO World Heritage Site. It is near City Palace and Hawa Mahal. The instruments allow the observation of astronomical positions with the naked eye. The observatory is an example of the Ptolemaic positional astronomy which was shared by many civilizations. The monument features instruments operating in each of the three main classical celestial coordinate systems: the horizon zenith local system, the equatorial system, and the ecliptic system. The name Jantar is derived from yantra, a Sanskrit word meaning instrument, machine, and mantar from mantrana, also a Sanskrit word meaning consult or calculate. Therefore, Jantar Mantar literally means calculating instruments. The first yantra you will see as you enter the Jantar Mantar is the Unnatamsa yantra, which is an instrument for measuring altitude, the angular height of an object in the sky. The large graduated brass circle hung from the supporting beam is the measuring instrument of the Unnatamsa. The brass circle is pivoted to rotate freely around a vertical axis. This ring has two cross beams in the vertical and horizontal directions. A sighting tube is pivoted at the center of the circle. It can be moved in the vertical direction to align it towards any celestial body. The rim of the brass circle has graduations marked in such a way that the smallest division is 1/10 of a degree. Large divisions of 1 degree and 6 degrees are also marked on the circle. This is the Dakshinotara Bitti Yantra. The Dakshinotara Bitti is an instrument built into a wall placed exactly in the north-south direction. The instrument measures the altitude or the angular height of a celestial object when it crosses the meridian. The meridian is the arc defined by the north, south, and the zenith. When an object crosses the sky, halfway between its rising and setting times, it is said to transit the meridian. This is the Brihat Samrat Yantra. The Brihat Samrat Yantra is the largest and most iconic instrument at Jantar Mantar, constructed by Maharaja Sawai Singh II in the 18th century. This monumental sundial, often called the Great King of Instruments, is a masterpiece of astronomical engineering. It serves as a highly precise tool for measuring time, tracking celestial objects, and determining declination and other astronomical parameters. The key metrics of the Brihat Samrat Yantra are: the Brihat Samrat Yantra is a large triangular gnomon, a structure casting a shadow, standing at 27 meters tall. The gnomon is inclined at an angle equal to the latitude of Jaipur, which is 27 degrees, ensuring optimal alignment with the celestial equator. The yantra's hypotenuse rise points towards the north celestial pole. Two large quadrants flank the gnomon on either side, which are aligned parallel to the Earth's equator. These are marked with scales for time measurements, accurate to 2 seconds. You can see the marked area in green here. Like the smaller instrument Lagu Samrat Yantra, the Brihat Samrat Yantra casts a shadow on the two east and west quadrants. When the sun is in the east, the shadow is casted on the west quadrant and vice versa. And as the sun is at the meridian or 12 o'clock position, the shadow is not visible for 2 seconds and then it moves to the east quadrant with the sun in the west side. As shown by the animation, when the sun is completely to the west side, the shadow is casted on the east quadrant, showing a time of 6 p.m. for example. As mentioned before, the Brihat Samrat Yantra has an accuracy of 2 seconds, and thus if we take a single curved marble stone with the stone representing an hour section, then this 1 hour section is further segmented on the marble into 4 15-minute segments. If we further take this one 15-minute segment, then this single 15-minute segment is further segmented into 15 1-minute segments. Then each 1-minute segment is further segmented into 10 6-second segments, and finally the 6 seconds segment is segmented into 3 2-second segments, giving this yantra an accuracy of 2 seconds. Another important aspect of the Brihat Samrat Yantra is that it is also used to measure the declination angle in north-south direction of planets, which is accomplished by a person walking on the steps up and down the hypotenuse of the yantra with a pole in the person's hand. This is then matched with the shadow of the pole on the 2 quadrants on east and west of the no moon, and then the angle scale is read, which is located along the hypotenuse of the yantra. It is also important to note here that the scale on the quadrants is finally marked for detailed readings with adjustments made to account for the equation of time, which is the difference between solar time and mean time. The sheer size of the yantra reduces errors caused by imperfections in smaller instruments. The Brihat Samrat Yantra reflects the advanced astronomical knowledge of 18th century India and Sawai Jai Singh's ambition to create a precise observatory. It is not only a scientific tool but also a testament to the synthesis of astronomy, architecture, and engineering. The area you see here is the Rasi Valya Yantra. Rasi Valya are instruments for measuring the celestial latitude and longitude of the celestial bodies. There are 12 instruments part of this yantra, which represents the 12 signs of the zodiac, one for each measurement to be done when the corresponding sign of the zodiac transits the meridian. Each unit consists of a triangular gnomon and a quadrant perpendicular to it, which is analogous to the Samrat Yantra. However, these differ with each other regarding to the shape and size of the angle of the gnomon. Celestial longitude of an object is measured along the ecliptic, while the angular distance of an object to the north or south of the ecliptic is its celestial latitude. Ecliptic is the annual apparent path of the sun in the sky. The gnomon of a Rasivalya instrument points to the ecliptic pole when the zodiacal constellation corresponding to that Rasivalya transits the meridian. At that instance, the celestial longitude of the object can be measured using the quadrant of the Rasivalya, while the markings along the length of the gnomon can be used to determine the celestial latitude. This is the Rama Yantra. Here we will understand at a high level about the Rama Yantra, which consists of two yantras as shown on your screen, one on the right hand side and the other on the left hand side. This combined yantra measures the altitude and azimuth of the sun. Altitude in this sense is expressed as angular elevation up to 90 degrees above the horizon, and azimuth is the number of degrees clockwise from the due north to the object's vertical circle. Here one can see the azimuth, which is shown by the green angular mark on your screen, and the blue angular mark on your screen depicts the altitude of the sun. Now looking at the two complementary yantras. The yantra on the right hand side and left hand side both consist of 12 segments and in total of 24 segments. Please note that the animation is not made to scale of the real yantra at Jantar Mantar. However, if we take a look at the right hand side yantra compared to the left hand side yantra, the right hand side yantra's segments are more wider than the left hand side because the right hand side yantra consists of 18 degree segments on each pillar, and the left hand side yantra consists of 12 degree segments on each pillar. Therefore, if we convert the degrees to time, we know from science that the earth rotates 1 degree every 4 minutes, and with this math we know that for 18 degrees this equates to 72 minutes, and similarly this converts to 3 gatis in Vedic time, where 1 gati is 24 minutes. This represents the time interval for each pillar of the right hand side yantra. Similarly, for the left hand side yantra, if we convert the degrees to time, knowing that the earth rotates 1 degree every 4 minutes, we can say from math that for each 12 degree segment, this equates to 48 minutes, and this converts to 2 gatis in Vedic time. Hence, this means that the shadow casted by the no moon towards the east or right hand side yantra, the shadow of the sun stays in the east for 72 minutes on the inner walls of the yantra, and the same shadow is casted by the no moon stays for 48 minutes in the west or the left hand side yantra. To see how the instrument works, let's take an example here when the sun is in the position shown on your screen. The sun casts a shadow through the no moon. The no moon shadow is then seen on the vertical pillars of the right hand side yantra, and then both the azimuth and altitude of the sun can be read with the help of the Devanagari numbers inscribed on the structure. Here, if you see the graph on the far right hand side of your screen, this represents the inscribed vertical lines and horizontal lines that you will be able to see on the vertical pillars of the yantra. In this graph, you will see that the vertical axis or horizontal lines represent the altitude measurement, which is numbered every 5 degrees, starting from 45 degrees at the right angle origin and then decreasing all the way down to 0 degrees, which is at the top of the vertical pillar. Similarly, the vertical lines inscribed on the pillar all the way around the circumference of the yantra allows us to read the azimuth of the sun from 0 to 360 degrees. This allowed pundits to understand when the sun completed a full revolution. The two yantras complement each other. When the shadow is not on the right hand side yantra, the shadow is on the left hand side yantra, and vice versa. This is due to the fact that the sun changes its azimuth and altitude throughout the year. Hence, during the olden days, pundits wanted to move in between these structures and yantras to take accurate measurements of the sun's position, and this was only possible by splitting the yantra into two halves, and hence Rama Yantra has two complementary structures, combining it to measure the altitude and azimuth of the sun. This is the Digamsa Yantra. This yantra is a cylindrical instrument that has a simple method of determining the azimuth of a celestial object. This is the Nadi Valaya Yantra, which is the last of the 3 yantras which we will understand in more detail as part of this video. The Nadi Valaya Yantra is an equatorial sundial of a simpler design from the Lagu or Brihat Samrat Yantra, which we previously illustrated in this video. But the Nadi Valaya Yantra performs a similar function. It measures the local solar time at the latitude of Jaipur. And in addition, the yantra can also be used to find the declination angle of the sun, the time of the day, and also to know whether the sun or other planets are in the northern or southern hemisphere. And hence this yantra has 2 dial faces, one for each hemisphere. Let's try to understand the fundamentals of the yantra at a high level. This yantra measures local time and consists of a thin rod-like gnomon fixed perpendicular to the masonry dial, which is shown in the middle of the dial. And this gnomon points in the angle of the northern celestial pole. In addition, the face of the dial is parallel to the Earth's equator. Taking a closer look at the dial is divided into 24-hour segments. And if we take a 1-hour segment from the dial face, we can see that 1 hour is segmented to 2 30-minute segments. Then the 2 30-minute segments are further subdivided into 12 5-minute segments. And then these segments are further subdivided into 5 1-minute segments. This tells us that the accuracy of this yantra is 1 minute. We must remember that during the course of a year, as the sun goes through its ecliptic journey, the sun stays in the northern hemisphere for 6 months and southern hemisphere for 6 months. And during equinox, we can see that the northern and southern hemispheres are activated on this instrument. During our visit to Jantar Mantar, this was during the winter season, so the southern hemisphere was active as the sun takes a shorter path. During the short winter days, the sun does not rise exactly in the east, but instead rises just south of east and it sets south of west. The way the dial operates is that when the sun is in the east, the shadow of the rod is casted to the west side of the dial, and when the sun is in the west, the shadow of the rod is casted to the east side of the dial. If we take a cross section through the sundial and focus only on the surface of the northern hemisphere dial, as visible to us in this animation, we can see that the surface of the dial is set at a 27-degree angle, which is the latitude of Jaipur. And hence, this specific dial is designed only for Jaipur due to the latitude dependent construction of the dial face. So taking this example, the image on the right hand side, we can see that when the sun is in the west position and the shadow is casted on the east side of the dial, we can for example say that the time is 6 p.m. in the evening. At noon, the shadow points straight down, which is also known as the meridian. It is also important to note that the yantra also consists of an additional Vedic time division, which divides the day into 60 gatis. Each gati comprises of 24 minutes. As we know, a day consists of 1440 minutes, and if we divide this by 24, we get 60 gatis. Moreover, the upper half of the yantra can also function in the moonlight, as this depends on the brightness of the moon and shine that the moon casts on the instrument. Furthermore, any planets that are close to the moon, we can see the shadow of the planets on the instrument, and this can also give us an understanding if the planet is in the northern or southern side of the instrument. This helped pundits back in the day to read the pulse of a patient through these inferences. Hence the name Nadi Valaya Yantra. As we come to the end of this video, there is one last yantra that we will see. This is the Dhruvadarshak Patika Yantra, which is the simplest of all the instruments found in the observatory. The instrument was used as a compass in the olden days. This instrument is in the form of a small trapezoidal structure whose upper surface points towards the pole star.